Thank you. So I wanted to start by just asking, who's actually seen a launch here? Is anybody? One or two? There's a few. Great. So this is the launch of the James Webb Space Telescope. I'll just let the noise run for a minute.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So I'll stop it there. And the point I want to make is that launches are really amazing. They're loud, they're noisy, you feel the ground moving underneath your feet. And sometimes really big launches like this one, you actually feel it in your bones. And this was a really interesting launch because very few of us could actually go to see it, where you were all stuck, basically in houses, or some of us got to go to some of the areas where we were watching the operations. And we're all wearing masks because it was Christmas morning, 2021, so right in the middle of COVID. And I was really surprised by this launch because I've been in this business 35 years. I've seen numerous launches, and I'll show you a bit in a minute. But this was the only mission where people from the street, all down the street I live on, and places nearby, came and knocked on the door on Christmas morning and congratulated us on this splendid launch, which showed on TV, I think, all over the world. And they, to a person, all said, well, we bet you're really glad that's happy and that's over, and now you can start doing science. And the key part of my talk tonight is just to show you that this was just the beginning, and normally this is the hard part. And once you've launched something, you can kind of sit back and relax once the thing starts to see the sun, and you get power on the solar cells, and then you do something we call go power positive, which means all the electronics come on and things start working. So we went power positive very quickly, but that was just the beginning. And then we had this 6-month odyssey. Some of us called it 6 months of terror, and you'll see why. And from there, we could start science operations. So that's what I'm going to talk about. So I'm going to basically just lay out, why we built Webb, what were the goals in building this very large space telescope, explain to you why it took another 6 months just to get this thing unfolded and assembled in a way that we could start doing science with it, and then talk a bit about some of the science that we're actually doing with this mission. So you already heard my CV, but I wanted to show this chart for just a minute. So I started my career, I went to University of London and then University of St Andrews in Scotland. And when I completed my PhD, I had the opportunity to go to Baltimore and work on the Hubble Space Telescope. So I ended up actually working on 4 of the servicing missions, and for one of them I was actually one of the team that built one of the instruments. And then after that, I was hired by the Goddard Space Flight Center by NASA, the real NASA, as opposed to the institutions that we fund to operate these missions. And Dr. John Mather, who subsequently won a Nobel Prize for finding the temperature of the early universe, had me become the project scientist for the observatory. So as I'm talking to you tonight, this is why I'm talking about this, because it was a really long 15-year labor of love getting this telescope from designing the first science requirements and then following that through as we worked with the engineering teams to turn science requirements into a real observatory. After we delivered the telescope, I actually moved into management and took over as Director of Science at Goddard, but I was still managing the James Webb Space Telescope project science team in that role. And now I'm the Director of Astrophysics, so I actually manage the science team that are running Webb, and you can see from this thing I call the swoosh chart, which has all of the missions that we operate or are going to operate in the Astrophysics Division at NASA. So we have an annual budget, which is on the public record of about 1.5 billion. And our job is to operate the science missions that we have flying, to develop the next generation of science missions, and then conduct research and technology programs with those missions. So it's a fairly broad portfolio, and we cover missions that study everything from gamma rays coming from merging neutron stars to studying the very early universe with the Webb telescope. So let me start with a story. So when Hubble was repaired in 1993, and they actually started getting real images, and for those of you who are too young, when we launched Hubble and took the first images, they were aberrated. It had spherical aberration. And that was a big shock to everybody, but NASA put a lot of work into figuring out how to fix that. And in 93, we launched Hubble in 90. By 93, we were able to put a servicing mission up that actually fixed the optics on the telescope by putting essentially corrective mirrors or lenses in all of the instruments. And one of the things that started taking people's attention almost immediately was when they took images of areas where there might be a star or a nebula, and then background areas that were dark, they weren't seeing things that were dark. They were seeing these sort of wisps or very small galaxies. And so one of my colleagues, Dr. Bob Williams, who was the director of the Space Telescope Science Institute at that time, decided that something needed to be done here. We were obviously missing something in our understanding of the early universe, and the only way we were going to find that out was by doing a concerted program of observations. So he put together a big review team, not quite as many people as in this room, but it was pretty big, and asked them for advice and said, how should we address this program? What should we do to figure out what these objects are? Should we do a very deep observation, or is that too risky? And they all came back and said, well, it would be great if you could do that, but we think it's risky. You could get fired, because is it the best use of observing time? Because if we had just fixed Hubble and, you could work out the sort of dollar per minute for the observations, and it was pretty high. So Bob decided he'd take a risk. And against all the best advice he got, he put 300 hours of Hubble time into doing what was called the Hubble Deep Field, the first very deep observation where we picked a piece of the sky that had no stars whatsoever, seemingly dark, but for a few galaxies that came up in short observations. And he did the Hubble Deep Field. And instead of finding nothing, we found this, 10,000 galaxies in this field. And as we started to study what was going on here, we realized that we were seeing back into the early stages of the universe. So basically what that means is, some of the galaxies in this image probably formed about 1 billion years after the Big Bang, because that's about the limit of where we can go with Hubble. So in order to understand why we know this, you have to understand the concept of redshift. So as the universe expands, light is shifted or stretched. And so more distant objects are redder, and the wavelength at which you see specific features move into the infrared, and infrared is heat radiation. So you probably know firemen wear infrared masks these days, or goggles. So they go into a smoky room and they can find the person who's passed out from smoke on the floor. So infrared is just heat radiation. So all that light from nearby objects we see in the visible, as you go back in time, is being shifted into redder and redder wavelengths, and then into what we call infrared, which our eyes can't see, but it's heat radiation. So if you want to look back in time using this technique, you need a telescope that can see infrared or heat radiation. And unfortunately, Hubble can only see back to a certain wavelength. So it can just see into the infrared, but not very far. And by this time, in studying these deep field images, we realized that if we could go deep enough and far enough back, we could actually peer back into the time when the very first galaxies and stars formed in the universe. The problem was Hubble couldn't do that. And the other problem was the mirror just wasn't big enough. Hubble's a 2.4 meter mirror, and we realized we needed something in the 6 to 8 meter mirror size to be able to do this. So this is how Webb was born. It was basically to try to find the very first stars and galaxies that formed in the universe, and then study how they evolved as a function of time by studying galaxies at different redshifts. But we also don't fly these really big, expensive observatories just to do one thing. So we want it to be an observatory, something that the whole science community can come and use and do whatever science area or discipline they're interested in. And so we also made sure, as we started thinking about the design for Webb, that we could maybe study the formation of stars in dark clouds. And one of the problems with Webb is it's a visible telescope, so it's the same radiation you see with your eyes, and you see all these beautiful pictures that Hubble took, but a lot of them are dark clouds of dust, and you can only see the shadows. You can't see inside. At infrared wavelengths, much the same as the fireman in the smoky room, you can see inside these clouds and see how stars are being born. And a very important issue in understanding that is, how do stars form? How are they born? What chemicals or molecules go into their formation? And then how do planetary systems form around them? So you really want to be able to study these dark clouds like the ones you see here. And at the top is the visible image of Barnard 68. And at the bottom, you can see an infrared image and all these stars appear. So we want to be able to study each of those stars individually in these big clouds. And there will be lots of different stars at different stages of their evolution. So we can really put together a picture of how this works and how planetary systems form around them. We were also lucky because just about the time we started doing the science requirements, people were starting to study planets around other stars. So one of the things that I spent a lot of time on while I was the project scientist was making sure that we will be able to study planets around other stars. And I'll explain to you later how we do that. But first, let me talk about what these science requirements then mean when you sit down to actually design a telescope. So the first thing is, if you want to study infrared radiation, you've got to be cold. So if you can only see the infrared radiation that's coming from your own telescope because it's, say, at room temperature, then you're not going to be able to see very faint heat radiation coming from the universe. So you've got to get that telescope really, really cold. And in fact, we go to 40 degrees Kelvin. So that's 40 degrees above absolute zero. And you probably know if you've ever put, hopefully you haven't, but if you put your iPhone in a fridge, you know, it stops working well before it gets to 0 degrees. You know, electronics and electronic systems don't like being cold. Mechanisms don't like being cold. And here we are talking about minus 230 degrees Celsius, really, really cold. And when you get to those kind of temperatures, everything you ever knew about materials changes. You have to basically go back and learn how even the most simplest material works and behaves at those temperatures. The other thing is we wanted a big telescope. So we finally realized that we could do the science we wanted to do with a 6.5-meter telescope. Unfortunately, and at the time, the Ariane was the biggest launcher available. 6.5-meter telescope did not fit in that fairing. So we realized we'd have to fold the mirror up to launch it. And that immediately means you've got to break the mirror into segments. So we came up with the design of an 18-segment mirror, and 3 segments on each side of the mirror would fold back, and you know, we could basically fold them around the payload for launch so that we could squeeze it into the fairing. And if you look up here at the top right in the video, you can see what the package finally looked like when we got everything sorted out. The other thing, and people always ask me about, well, why can't you service this telescope? The middle panel on the right is why you can't service this telescope. When you build things to work at cryogenic or extremely cold temperatures, you have to do a lot of work covering them in what's called multi-layer insulation and really focus on making sure they can get to the right temperature. And so that really excludes the notion of putting them in a box that you can just pull in and out like we did on Hubble. You really have to gift wrap each piece of hardware individually, and you're slowly building up these instruments with all this gift wrapping on them, and then you put them in a structure like the one you see there, and there's no way you can tear that apart in space and put a new instrument in. So there was no way we were ever going to be able to service this mission from day one. The other thing that I want to mention is this had a new concept. So we wanted it to be an observatory, as I said, and that means that it has to last more than a couple of years. So NASA had flown a few infrared telescopes, and they were pretty small, and the way we got them cold was to fly them with a big dewar or drum full of liquid helium. And that liquid helium slowly boils off, and when it's done, you don't have a cryogenic telescope anymore. You have a room temperature or a warm telescope. So we didn't want to have this run for just 2 years. So we came up with a new way of thinking about how we get these things cold, and that is that you have these massive membranes, and you'll see more about these as we go through the talk, that would allow you to shield the telescope from the sun. So you fly this telescope so that the telescope and the instruments are always looking at cold space, and the sun shield basically protects them from seeing the sun so that they can actually get cold. And I'll come back to just how challenging that turned out to be as we go through the talk. But that's basically how it works. As I said, the problem is you can't fly it like this. So then you have to fold everything up. And as you start to look at what it takes to fold it up and then unpack it again once it's in space, you start to realize there are a lot of challenges that kind of creep in as you do this development work. It's kind of a reverse origami puzzle. That's how I always thought of it. So the first thing is the mirrors. So as I said, we built a mirror made of segments. Now, this had been done on the ground already at the Keck Observatory, but they didn't need to fold theirs up to take it anywhere. They took it to the mountain piece by piece. We couldn't do that, so we went with a concept where we could fold what we called 2 petals around the side. And again, we come back to that temperature. Glass really didn't work that well at those temperatures, so we realized we'd have to use a different material, and we finally settled on beryllium, which is a really nasty material. It's carcinogenic, and it's very hard to polish. So normally with glass, you polish away, and you do a measurement. Have I got to the right prescription? If not, then you do another measurement, and then you start polishing again, and you just follow that cycle. Beryllium doesn't like that, because as you polish it, you're putting stress in the material. Beryllium's kind of like a ceramic material. So before you can do a measurement, once you've done your polishing cycle, you have to bake it. And then it's different from what you thought you had before you baked it. So as you polish these mirrors, you're in this iterative scheme where you just keep going and going until you get to the number you want. So that sounds fairly simple. But the other problem that we faced is that we were going to operate these mirrors at 40 degrees above absolute zero, but we're polishing them at room temperature. So you have to do something called cryo-polishing. So you've got to actually start by figuring out, what do I need to polish into this mirror so that when I then cool it down to 40 degrees above absolute zero, it's got the right prescription or figure, as astronomers call it. And so you end up having to develop these very sophisticated mathematical models, which work very well until you have to do that annealing or baking stage. And that then makes things a lot harder. The 2 mirror images you see on the far right are what the mirror looks like at ambient temperature and what it looks like when you cool it down to 40 above absolute zero. And I'm going to just do a quick segue. So we polish into these mirrors a figure, which if you ever go to the opticians, they call a prescription. And the way we determine how well we've done is what is the average deviation from the perfect prescription. And we call that wavefront error. So to give you some idea of what we're doing here, each of these segments is about 1.5 meters. The faceplate or the surface of the mirror is about 3 millimeters thick. And we are polishing them to 20 nanometers. Now, if you haven't heard what a nanometer is, it's 10 to the minus 9 meters. And just to give you some idea of what that means, a typical virus, single virus cell, is about 30 to 50 nanometers across. So we're polishing a 1.5 meter size mirror segment, and the overall error in the polishing from the perfect prescription is about size of a virus. So that's what we had to do. But then we're trying to make sure that that's what it looks like when it's cold. So on that figure just here, the ambient surface, that's about 100 nanometers. But then when you cool it down to 40 above absolute zero, you get your 20 nanometers, which is what we're looking for. So everything, when you go to cryo or cold, gets so much harder, and you have to stop and think about how you're doing things and how you're making sure that you're not putting in errors. The other thing I wanted just to emphasize, I showed you that chart of what I've done in my career. And one of the reasons I showed you that is just to emphasize an important value that we have at NASA, which is knowledge management. And what that means is every time you do a program, you walk away when it's done and you write down all the lessons you've learned. How am I not going to mess up next time the way I did on the previous program? And the big one for us on this program was, how are we not going to have another Hubble-like error? You know, we used to joke that the ghost of Edwin Hubble was sitting on our shoulder as we did this program. So how would we avoid the errors that they made when they were polishing the Hubble mirror? And it was very simple. You do cross-checks. But they did cross-checks on Hubble, and when they got the results, they were so far off of what they expected that they were disregarded. They just said, well, we probably didn't do everything right in the test. So we did cross-checks on every single mirror, and we set the criteria for the checks before we did the measurement. And then if they didn't conform to what we expected, we went off and figured out why. We didn't just say, oh, we probably messed up the test. So every single piece of glass, or beryllium actually, on this telescope was tested and cross-checked with a separate technique. So that presented some challenges, because some of the measurement hardware, we could only find one company in the United States that would make it. So we ended up having to commission other companies to make some of the test hardware, so we'd have two different versions of the test hardware to verify that the mirrors did have the right shape. So a lot of challenges there. Now, if you've got 18 mirrors, I guarantee you, and you'll see when I show you what they look like when we got to orbit, they are not all going to be perfectly aligned when you get to orbit. Just the horror of being launched means that, you know, these things are getting shaken, they're seeing, you know, tens of Gs, and they move. So each of our mirrors has actuators on the back which are able to move them at nanometer steps so that we can adjust them. And those actuators give us 6 degrees of freedom. So we have piston, which is up and down, tip, tilt, and rotation. So we could adjust each of the 18 mirrors and then get them to become a perfect 6.5 meter mirror. So by the time we got to the overall mirror, the error for the, or deviation from the prescription, was around 80 nanometers. So twice the size of a virus across a 6.5 meter telescope. So really challenging numbers here, and really pushing the limits of what our technology partners, Northrop Grumman, Ball Aerospace, a whole host of companies that worked with us on this program could do and even measure at the time. So even simple things like, how do you measure that kind of deviation from a perfect prescription without building really sophisticated test setup? We went to industry and we told them what we wanted to do. And that primarily was that we wanted to be able to test them even in a room like this and not have to worry about putting them on, you know, special benches that were isolated from the building and isolated from, you know, people driving past the building in trucks. And they came up with a very high-speed imaging technique that allowed us to test the mirrors wherever we wanted. And that technique is now being used to do LASIK measurements. Because when you go to the optician and you put your head on the thing and they do the measurement of your eye, your head, you know, from their perspective is moving all over the place, and so is your eye. So being able to do these very high-speed measurements is a great way of improving the quality of the measurements of your eye they do before you then go off and get a LASIK treatment. So there's a lot of things that we took out of this in terms of technology breakthroughs. The other big problem with the mirror, again, coming back to Hubble, is you want to test the mirror as you're going to fly it. And that is extremely hard. So after much searching, we came to the conclusion that there was only one place where we could test the mirror, and that is Chamber A, which is at the Johnson Space Flight Center in Texas, and not the best place if you go there at the wrong time of year, as we found out, because we ended up doing all our testing while there was a hurricane raging outside. But Chamber A hadn't really been used since the Apollo era, and I put a picture on the right there just to show you how big it is. I mean, that's the Apollo command module and its assembly sitting there in the door. This thing has an enormous door. And so we had to go in there and figure out, one, how we were going to renovate it, because it's a national monument. And we spent a lot of time talking to the national parks about what we could and couldn't do. But one of the other things we had to do is figure out how are we going to get that telescope to 40 above absolute zero in that chamber. So we had to build a lot of hardware inside the chamber, a big shroud that we pumped liquid nitrogen into, and then inside that we had a second shroud that we pumped liquid helium through. And the telescope then went in the center of this assembly and basically hung from the ceiling. And one of the things we learned is that if you've got everything sitting on motors, you don't actually need to go back and perfectly align everything and get an image through the whole system. You just need to make sure that you're in what's called the capture range of all the motors. So we've also changed the paradigm for how you prepare these segmented mirror telescopes for space. You basically just make sure that every mirror is sitting right in the middle of the motor range so that you can do the adjustments you need to do to get them aligned. So that's pretty cool. So it does bring some other problems, though, when you're building a telescope this big, and people kind of forget that you've got to move it around, So for just the telescope, we had to go to Huntsville in Alabama to test the mirrors, and then we had integrated it and built it at the Goddard Space Flight Center just outside Washington. Then it went to Space Park in Redondo Beach at Northrop Grumman, and then it had to go to French Guiana for the launch. So you very rapidly find that it's really hard moving these things around. So we ended up within the United States flying it around in one of these big C5 transporters, and you can see it at the bottom. And one of the things that keeps me awake these days is it just fit in the C5. You can see that big white container, the telescope is inside that. And it's just being sort of driven into the back of the plane. And there's a picture on the left that just shows you what the inside of the plane looks like. So the next big telescope we build, if it's bigger, we've got to figure out a new way of moving it around the US in order to prepare it. The other problem with these big containers is when you want to drive them from Space Park in Redondo Beach to Long Beach to put on the boat, you've got to shut down freeways in LA, which doesn't make people very happy. So we tried to do as much of that as we could at night, but you still have to shut streets, and that you need big array of police vehicles in front and behind, making sure that it's protected as it goes all the way to Long Beach. So I don't think we made too many friends in LA that evening. And then we put it on a boat provided by the European Space Agency, and it goes down from California through the canal, the Panama Canal, now into the Caribbean to go to French Guiana. And we didn't fly it down because when we went to French Guiana, we found that if we took it by plane to Kourou, there was no way we could drive it in the same way you see we're driving it around LA, because there was a lot of very small roads, a lot of bridges that wouldn't take the weight, and a lot of low electrical lines between Kourou and the launch site. So in the end, we said, no, we have to take the boat straight to the launch site, and that's what we did. So even the simple stuff like moving things around when you get to this scale get to be really, really hard. So that's another lesson. So this is the other, I think, really exciting part, and I probably spent 3 or 4 years on the requirements for this. So that's actually me standing right in the middle there as it was being assembled, so you can see how big it is. When we say tennis court size, we're not joking. It is enormous. And the material is Kapton. So it's just the same as those metallic birthday balloons that you get. Very pliable material. It's slightly thicker than the material on the balloons, but not by much. And one of the things we found almost immediately is you cannot just fold this stuff up, into piles and wrap it around the spacecraft, because as the rocket launches, it rips, the air leaving the fairing will just rip these things to shreds. So, oh my God, you have to fold it up and then somehow figure out how to pin it down for launch so it doesn't tear to pieces. And it turns out you have to put covers on it as well. So we spent a lot of time figuring out how to package it for launch. And then you've got 5 layers here. So we could probably get away with 3 layers. But if you're going to be resilient to micrometeoroid impacts over the life of the mission, you really need 5 so that you maintain enough margin on your thermal performance. So 5 layers, and they all have to be separated at the right separation. And the really hard part, and you can't really see it too well in this figure, but each of those layers has to be separated by a certain distance with respect to the others. So the bottom layer is actually pretty warm because it's looking at the sun, so that cannot see the telescope. And so on and so forth as you go up the stack. So the bottom layer has to be aligned with the next layer by about 2 centimeters on each side, and then the next one has to be 2 centimeters on each side. So you can imagine trying to pull out this massive structure in space, and when you tighten everything up, you've got 2 centimeters alignment on the sides for each of the layers. So really interesting problem. And all of those pins, of course, are going to be what we call single point failures. If one of them doesn't fire and release, then we can't unfurl the sun shield. And that's the end of the mission. So really nerve-wracking. So it took about 110 of these pins to hold everything down on each side for the launch. Now, this is the traditional Wimbledon way of covering tennis court size hardware, but we took a different approach. And this will just show you what happened in that 6 months after we launched. So we start with the origami puzzle. And first thing is the solar array, which went out almost immediately as it happened. 2 hours after that, we have to put an antenna down so we can talk to the world. And then after 3 days, we start working on this sun shield. So the 2 sides are pinned down to these pallets, and they came down about 4 days after launch. Then we lift the telescope off of the spacecraft bus, which is that big square box, because it cannot be in contact with all that hot electronics. We've removed the covers, so the covers are held on with these pins. You fire the pins, and the covers basically roll themselves up. And then you start pulling it out like this. And it's very nerve-wracking watching this. On the computer, when all you can see are the tensions in the cables and people sort of going through the steps, but you can't see any of it. So we couldn't see this, and you can't put a camera anywhere because it will then become a source of heat, which will prevent you doing your science. So no cameras, and we just had to keep testing this on the ground until we understood how everything worked, and then we knew what was happening during launch. And there you see the last 2 wings of the mirror come around. So even the secondary mirror has to be folded up for launch. So everything on this telescope is deployed after the launch. And just to give you a quick idea of what that looks like, so this is a highly compressed and edited video just showing you a few of the highlights. So you can see the telescope here just being slowly lowered down. And then you can see the tensioning of those sunshield layers. And you end up with a very highly tensioned set of layers that are properly aligned with respect to each other. And that's the back of the telescope where the instruments go. So what does that look like? Well, it looks like this: 50 major deployments, 178 of those release mechanisms, 155 motors, and over 600 pulley assemblies. So that's really a lot of hardware. And that, when you added everything up, came to about 250 single-point failures. Now, normally on NASA missions, or certainly science missions, we will have maybe 5, 10 at most. So 250 is pretty scary. And those release mechanisms, I was going to bring my umbrella to demonstrate, but basically they're pins, and you have a wire wrapped around the pin, and then a little fuse at the bottom, and when you fire it, the fuse melts and the wire unwraps and releases the pin. So 178 of those, and 100 were holding the sun shield down. The rest were holding the telescope for the launch phase where it's getting shaken really badly. And that's because this is what some of my engineering colleagues call a floppy structure. Now, it's not, but for an engineer who sort of likes working with really stiff structures, this telescope is floppy, so everything had to be pinned and locked down for launch, so when we shook it, it didn't all come apart. And we weren't done there, so once we had finished all those deployments, we still had to lift all 18 of the mirrors another 3 centimeters off of their sort of launch location. So we had to sort of piston them all up by about 3 centimeters, and then we started the alignment, and this is what it looks like once you've got all the mirrors aligned. We were lucky that we didn't have to go hunt for any of the images, but this is how we aligned the telescope. So you start with 18 of these images, and then you start stacking them one by one, and each of these requires a separate observation, a number of calculations, and finally we get to merge them all into a single spot, and then we do a final calculation based on the spot. And for me, one of the great ironies is that the technology that we use to do this is a technology we developed, or I would say matured, after trying to figure out what was the required prescription to fix the Hubble Space Telescope. So it's a technique called phase retrieval, where you measure out-of-focus images on both sides of the focal point and use those to calculate what you need to do with the mirrors to get everything aligned up. And when you get it right, you get to a spot. And this is what it looked like. So this was a really interesting exercise for our press people, because when we planned this program, we were going to do a press release on a star. We've phased the telescope's seeing a single star, everything works, good to go. And this is the image they took. This was a few seconds, and you can see all these galaxies in the background. And so the press people were saying, well, what do we say about those? So we had to basically rewrite the whole script for this first press release that said we've got the telescope aligned, and point to the fact that clearly we were doing much better than we thought we were in terms of the image quality and the sensitivity of the telescope. And in fact, it turns out, as you can see there, the telescope's image quality was 2 times better than we expected based on the modeling. The image jitter, which contributes to that, which is how much shake the image has because the spacecraft has a lot of moving parts in it, gyros, things like that, was 7 times better than we expected. 7 times better than Hubble, in fact. And the sensitivity turned out to be 30 times better than the requirement. So in a few second image where we expected just to see a star, boom, all these galaxies appear, and everyone's like, wow, what's going on here? And it's hard to appreciate what this means, especially when you think about what we had before in infrared astronomy, but this next image really shows that. So the image that's being covered over was taken with the Spitzer Space Telescope, which has a 0.5 meter mirror, which is about the size of the secondary mirror on Webb. And you can see the same field being uncovered from Webb, and the difference is just mind-blowing. I mean, there's no other way of putting it. So once we started getting to the point in the commissioning where people were seeing real science, they were jumping up and down in the corridors, everybody was giddy, and you couldn't find somebody who wasn't smiling in the building. It was just amazing. So you see what that mirror... So this is just a sea change, and this is one of the reasons we build these telescopes, to really open up new discovery space. So it went on and on. So the next thing, I'm not quite sure what that is, but sorry, there's a little blue thing here that wasn't there when I made the slide. So the very first science images we take with new telescopes, we call the early release observations. And we did 4 with Webb. And we'd done pretty much 4 with all the Hubble instruments before that and other missions that we launched. On this telescope, the first image was so amazing that the White House wanted to do the release. So we actually did the press release from the White House. And you can see President Biden standing there with the big backdrop of the James Webb Space Telescope, and we presented this image, which even today just amazes me. And what you're seeing here is something that amazingly Einstein predicted back in, I think it was 1918, and speculated that nobody would ever actually be able to confirm his paper. And basically the idea is that when you have very large mass, it can bend light. And so what you're seeing here is a supercluster of galaxies, and those are the white galaxies you see in this image here. And the mass of that supercluster is such that it is magnifying and bending light from galaxies that are much more distant than the supercluster. And it's kind of illustrated here in this schematic. So you see this field, it has lots of whitish galaxies, which are the nearby galaxies in this supercluster. And behind them, or superposed on the field, you see all these red wisps. And these are the highly distorted images of galaxies that are way, way behind the cluster. So, we're also getting a free bump in sensitivity from nature here as well. And the thing that really I found just almost shocking is that this image from day one, normally we do what we call a few press releases, we publish the pictures, everyone says, yep, it works, and then we move on and start doing science. People were doing science with this image hours after it was taken, and it is still producing new papers in the literature. And I'll show you one example in a minute. But we also got a lot of attention. So the first images showed in Piccadilly Circus. You can see there on the left. They illuminated the Empire State Building with gold light. Coldplay showed the images at their concert that week. And you can see Times Square also showed the images. And a couple of weeks later, Jimmy Buffett showed the images at one of his concerts as well. So we got a lot of airplay for these very first images. And I said I'd show you some of the science. So that very first image, you can see this feature here magnified, and on the right there's the Hubble view of it, and on the left is Webb. And astronomers immediately dubbed this thing the sparkler. And it's just amazing, because what you're seeing here, all those little dots, it's a very distorted image of a background galaxy, and it's surrounded by globular clusters, very large, dense clusters of stars. And you can actually see the globular clusters in this galaxy. And we think these globular clusters probably formed about 350 to 400 million years after the Big Bang. So even with this very first image that we did for the press release, we're already starting to get back to that very first epoch when stars and galaxies were born. So that was really, really amazing. And right now, this is the record holder. This is the most distant object we found with Webb. It has the usual sort of telephone number nomenclature. We're not very inspirational when it comes to the names of these objects. But it demonstrates that we really are pushing back to just that time when the very first stars and galaxies formed. And what you see on the right is a spectrum. This is what you get when you pass the light coming from this object through a prism or reflect it off a grism to disperse the light into its, the colors that make up the spectrum. And that allows us to confirm that this really is an object that old. So it has a redshift of 14.3. So that's pretty amazing too. The other things I talked about, I'm going to briefly mention the formation of stars. So one of the other early release objects was this image at the top called the cosmic cliffs. And it seems to be very popular on T-shirts. I've seen at least two people today wearing cosmic cliff T-shirts. And you can actually see in this image, see inside the cloud and start to study the formation of stars, through all the different processes. And I put a few examples at the bottom of other observations. The ones at the bottom are not from the cliffs, but the first two, the Herbig Haro and the protostar, are both star systems that are about a few tens of thousands of years old. And then on the right, this is Fomalhaut. It's the second brightest star in the southern sky. And you can see this big disk of dust that is orbiting around this star. And this is debris left over after planets have started to form. And the new result from... there was a mention of this at the beginning. I was on the team that discovered this debris disk. And the new JWST image shows that there's actually an inner gap in this system that we didn't know about. And then there's another disk of warmer gas closer to the star. So we're really starting to understand how stars form and how those planetary systems around them form. My colleagues in the solar system scientific discipline would not forgive me if I didn't show at least one result from our own solar system. And I think this one is timely. We just launched a mission to go to the moon Europa. This is Saturn's moon Enceladus. And we knew from a previous NASA probe called Cassini that there were these plumes of liquid coming off of this moon. And you can see in the top left, that inset gray image, there's, I think, 3 or 4 little fingers or plumes. That's actually liquid coming off of this moon. And what we think is that it's actually got a big sea that's covered by ice. So the outer shell is ice, and there are cracks, and the liquid underneath is spraying out. So we knew from Cassini that there were these things people call plumes. And then we observe it with Webb, and we find these are not plumes, they're torrents, just masses of water coming out. And they're basically seeding the E-ring of Saturn's ring. So we were able to do a number of measurements showing that this water is coming off of this moon and then going into orbit around Saturn as a part of this ring. So this is really interesting because one of the things that we'll be doing in the future, either at NASA or the European Space Agency, is going to this moon and trying to sample this water and see if we can find evidence of molecules that might indicate the presence of life in this moon. And then we come to exoplanets. So exoplanets are the really big thing in astronomy right now, studying planets around other stars. And there are a lot of them out there. We now know there's about 5,000 confirmed planets around other stars, and around 4,000 of those are in systems, which means there's more than one. And we study them with James Webb using this technique called transits. And I'm going to talk a bit more about this in a minute. But the basic idea is that this is a mini eclipse. So as the planet crosses the face of the star, if you're correctly aligned with respect to the orbital plane of the planets, you get a little dip in the light. So you can tell there's a planet there just from the dip. So a Jupiter-sized planet gives you a 1% dip in the light. An Earth-sized planet gives you 0.01%, really small and hard to measure component. But the really amazing thing about this technique is that if you then put that light through a prism, you can actually back out composition of the atmosphere of the planet. And this is one of those subjects where you do exactly what your math teacher told you not to do, which is to subtract two very large numbers. So we've actually refined this technique over the last few years in NASA and also in the ground-based community. And we're able to make these measurements. And Webb is ideal because you need lots and lots of light. So this is one of the very first exoplanet measurements. It's a star called WST 39, and 39b is the planet. And you can see this spectrum. So the bottom axis is wavelength, and then the side axis is signal level. And what you're seeing here is all the different elements in the atmosphere of this big, puffy, Jupiter-like planet. And one of the really interesting things is that JWST is so sensitive. Over here, you can see sulfur dioxide, which is produced by photochemistry, which is when the atmosphere of the star is interacting with the atmosphere of the planet. And this is something we often associate with the possibility of future habitability. On this planet, it doesn't, because it's big, massive, Jovian-sized planet. And we're also able to do small rocky planets. Those are a lot harder, but one of the things we can do is actually look at the thermal emission and figure out whether this is just a rock with no atmosphere, like Mercury, that's radiating heat, or whether this small rocky planet has an atmosphere. So JWST is starting to study a lot of planets. Now, most of the planets it's looking at are in the top box, what we call red dwarfs or late M spectral type stars. And they're relatively small, so a lot of red dwarfs are about the size of Jupiter. So you see a bigger signal when the planet goes across. JWST cannot study stars like our own sun, bigger, hotter stars. So if we're going to study those and look for evidence of life with those, we need to do something different, and that's direct imaging. So in the last few minutes, I'm just going to talk about what we do next, how we take the lessons from this mission and apply them to what we're going to do next. And I don't get to decide what missions we're doing as the director of astrophysics. I have a National Academy's decadal survey that's done once every decade, and the whole science community comes together and decides what are the priorities for this decade. And they write something called a decadal survey, and that is used by Congress as they think about how to fund all the different science disciplines at NASA. So Earth science, heliophysics, planetary, and astro all get our own decadal surveys. And it's very hard to get something funded if it's a big flagship like Webb, if it's not number one in that decadal. So it's been a very successful process, because it means you have the whole community behind you, and Congress know where to go to look to see what the priorities are. So the 72 decadal gave us Hubble. The 2000 decadal gave us Webb. We're just finishing up the Roman Space Telescope, which was the 2010 decadal. And my job is to implement the 2020 decadal. And that is a number of things, but the big flagship mission is to build a telescope that will search for life. So I'll just let this little video run for a minute. One of my colleagues put this together as the trail of the next mission. And it's kind of slow. Here we go. So this is what we're looking for: small, rocky planets that are habitable and might potentially have life. So one of the good things about being director is you get to pick the working names for these new missions until they give it a formal name. And this one, as you will see in a second, we are calling the Habitable Worlds Observatory. So I think that's a great name, because I don't need to explain to you what it's going to do. You can figure that out from the name. And that's really important, believe it or not. So what are we actually going to do? So back in 1935, a French astronomer called Bernard Liot wanted to study solar eclipses, but he didn't kind of want to wait for them to happen. So he came up with an instrument called a coronagraph, which basically did what a solar eclipse does, except he had an instrument with a small dot, and he blocked out the sun using that small dot. And then he could study all the structure around the sun. And this was a photograph taken from the last solar eclipse, and you can see these solar prominences and flares there. So this has become a technique that we use for doing astrophysics now. And what we want to do is take, instead of using the transit technique, is to use direct imaging. And that means we can study all types of stars and look for small rocky planets with atmospheres that are in an area where there might be the possibility of life. It's a very challenging problem because if you're going to look for a Jupiter, you need a contrast level of 1 billion. And if you're looking for small rocky planets like Earth, you need contrast level of 10 billion. And you can put your thumb around one of the lights here, look through it with one eye. That's basically how this technique works. But we're not just trying to block out a light so we can see the clock or whether they clean the ceiling. We're trying to find small rocky planets. And it's very challenging because they're very close to their parent stars, and their parent stars are much, much brighter. So this is the challenge. And what it means is that we have to go back and look at what we did on Webb and figure out how do we go from the Webb telescope to a telescope that can see small rocky planets. And it turns out that you have to be 1,000 times better in the prescription of your mirror than Webb. And it has to stay that way. So one of the things we did with Webb is we realized we didn't need to keep that figure by continuously adjusting it. In fact, we can't do that. But we would come back every 2 weeks and just tweak them, do a measurement, tweak the mirrors to keep it perfect. Turns out that Webb is so stable in space that we don't need to do that more than once every 2 or 3 months, which is pretty amazing. But with this telescope, we need to do it continuously, which is why it says active control. So we have to actively control the mirrors. So we're continually making those adjustments that on Webb we do once every 2 or 3 months. And we're trying to go a factor of 1,000 better than Webb. So I've got there the stability has to be in the picometer level. What does that mean? Well, it means that we're trying to get down to about the size of hydrogen atoms in terms of the overall error in aligning the telescope. And we're trying to do that continuously all the time. So this is the challenge for the Habitable Worlds Observatory, building what we call an active telescope that will be able to do these corrections continuously so that we can maintain the quality of the mirror and then use the coronagraph to image the small rocky planets. And we'll survey the nearest several hundred stars to our own solar system looking for planets like our own. What we do when we find them, well, we'll look for something called biosignatures. So a very famous US astronomer, Carl Sagan, and I'm actually really proud to be here tonight because I remember when I was a kid watching him talk right here about Mars on the television. So it's kind of cool. But Sagan figured out that he needed something to do while his missions were going to Cassini. So you saw a result from the Cassini mission and to Mars. And he had the idea, well, if I turn my mission back and look at Earth while it's on its way to Mars or to Jupiter, can I tell if there's life on Earth? And he basically made these observations and he found some of these biosignatures and concluded, yes, you could infer the presence of life by looking back at the Earth and taking spectra. So the kind of things we'd be looking for once we found these candidate small rocky planets with potential habitability would be oxygen, methane, carbon dioxide, water, what chemists call disequilibrium, and also potentially Rayleigh scattering as well. But we have to be smarter than that because, as you probably realize, different ages of the Earth, the atmosphere is very different. So we have to build a telescope that can not only pick and find biosignatures that look like our Earth today, but also like our Earth when life was just starting. And you can see the simulated spectra for 3 different ages of the Earth. So we're still doing a lot of research to figure out what exactly we need to do with this telescope. And we're just getting started now, but this is the overall goal. And I'm going to finish up by just quoting from the National Academies who came up with the recommendation to go build this telescope. And it says, if planets like Earth are rare, our own world becomes even more precious. And I'll let you read the rest of it. But the one I like is Carl Sagan, who said, the universe is a pretty big place. If it's just us, that seems like an awful waste of space. So I'll finish there, but one thing I hope you sort of take away from this is that everything we do on these big missions is inspirational. And I was talking to a gentleman on the way in who was telling me, he remembered the Apollo program and watching that as a kid, and so do I. And I have people working for me now who had that same experience with the very first Hubble images, and I'm sure in 5 or 10 years there'll be people working in astrophysics who remember the very first Webb images. So what we do in NASA science, and not just astrophysics, but all the science we do, is really inspirational. Obviously, we make a lot of discoveries. Hubble completely rewrote the textbooks in astrophysics. It won 2 Nobel Prizes, and I'm sure Webb would be just as successful as we go forward. But there are other things. People often say, well, why spend all this money? So the other thing that these big programs do is they really infuse, certainly in the United States, technology into industry. So we have queues of the biggest industries, the big aerospace companies wanting to work with us because what we do really challenges them to go to a new level of, technical capability, and that then, of course, flows out into all the other things they do. So, these pushing the envelope on technology really infuses, the nation's technical capabilities. And then finally, and I mentioned this a bit already, it really engages the next generation in STEM. So astronomy is one of the most accessible sciences, and we really think that we do a great job, certainly in the US with the programs that I manage, bring in kids from very diverse backgrounds into science or engineering or even program management, to work on these programs. People want to come and work on these programs because they're so much fun, they're exciting, they're obviously very stressful sometimes, but that's part of the fun when you finally get to see those first images. So I will finish there and take questions.